if you constructed, suppose you constructed a sequence of random variables, and the index for the sequence of random variables tells you the sample size used in constructing a particular realization. So that, for example, if you had x sub 10 of omega, omega is the sample that you collected. The 10 tells you that there are 10 elements in it, and x is the random variable you constructed out of those 10 observations that you got. So you did it for the index equal to 10, 11, 12, blah, 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 blah. And you're asking the question of whether or not, and then you measure the difference between the realization of the sample that you got, the random variable you constructed, and some number that we'll call theta. And so you construct the absolute difference between xt of omega and theta. And you do it for t equal to 10, t equal to 11, t equal to 12, so on and so forth. And you line up all of those differences till you get to, I don't know, 1,000. And I say to you, suppose that I want your random variable to be within 0.01 of theta. How big a sample would you need to guarantee to me that that would happen? Well, not guarantee, but it would happen with very high probability. Could you figure out an appropriate sample size? Could. So you couldn't guarantee it, but it would be very likely. So then I ask you, let's call the set A the union of all of that sequence of intervals that you found. And I ask you, as the sample size gets large, what's the probability of that union differing by more from theta, by more than epsilon, or less than epsilon, the one inside the ball. So you're looking at the probability, you're asking a question about the probability of a limiting sequence. Where else did we combine limits and probability? We talked about it actually last week or the week before. Remember where else we talked about limits and probability, or limits and probability? A couple of weeks ago, didn't we talk about small sample properties? Or maybe last week we talked about small sample properties. She's going to let you sink. Didn't we talk about small sample properties last week? Do you want to translate it? Maybe she doesn't understand what I'm saying. Did we talk about small sample properties last week? And we also talked about a couple of large sample properties, right? Do you remember what specific small sample properties we talked about? Do you remember what small sample properties we talked about last week? Didn't we talk about unbiasedness and efficiency and sufficiency? And what large sample properties? One in particular. We talked about consistency, right? And what was the notion of consistency? The sample statistic is consistent if it converges in probability to the population parameter. So we said, we asked the question, what's the probability that our sample statistic, based on a sample of size t, differs from the population mean by less than epsilon? For any given sample size, we just calculate that probability. Right? So we could, by choosing different sample sizes, we could construct a whole sequence of probabilities. And we then ask the question, what's the limit of that sequence of probabilities? Right? We had limit from t to infinity of the probability that the sample mean differs from the population mean by more than epsilon. And if we said that the probability of this differs from the population mean by more than epsilon, in the limit, that probability differs by more than epsilon, in the limit, then it's not consistent. But if the probability vanishes, becomes vanishingly small, as the sample size gets large, then the sample statistic might be simple. Right? So convergence in probability had something to say about the convergence of the sequence of probabilities. Convergence almost surely turns it around and says, what's happening to the probability of all those limits? So we construct a sequence which is, for convergence almost surely, so little omega is the sample space, is a realized sample based on a sample size of t. Mu is some population parameter of interest. And we look at the absolute deviation of our sample statistic from the population parameter that's of interest to us. And we say that for a given t, there are many such omegas that satisfy that. And we could construct a whole sequence of those. For a given t, we could find all the possible samples for which that's true, right? We could do it if we had enough time. It probably would be a simple experiment. If we'd had 3 coins, for example, we wanted to know the true easy to enumerate the sample space and figure out whether or not a given sample satisfies this inequality, where you get to pick epsilon as small as you want. And then we're going to make a sequence of those. So we find all the samples of size t that satisfy the inequality. And then we go ahead one more, to t plus 1. And we look for all the samples that satisfy that inequality. And then we go to t plus 2, and we find all the samples that satisfy that inequality. And we do that over and over and over again. And we put them all together, and we'll call them the set A. The set A consists of all the omegas, all the samples for which that's the limiting sequence. And then we say that xt of omega converges almost surely to mu if the probability of A is 1. What that's telling you is that we have a barrel here, and in this barrel I used samples of size 10. And whenever I took a sample of size 10 and I was able to satisfy this inequality, I put that sample in the barrel. And then I got another barrel where I was making up samples of size 11. And for every sample of size 11 that satisfied that inequality, I put them in that barrel. And then I went ahead, I don't know, 1,000 more observations. So I had x sub 1,000 of little omega, and I found all the samples of size 1,000 that satisfied that inequality. And if a particular sample, size 1,000, satisfied that inequality, I put it in the barrel labeled t equal 1,000. And then I asked, when I get out there and I line all these barrels up, starting here in Philadelphia, and I line them up sequentially until I get to the North Pole. And the barrels are about this big around, so there are, who knows how many in here in the North Pole. There must be over 1 million of them. And then I asked, what's the limit of the sequence of those absolute differences? And then I asked, suppose that I cover my eyes and I reach in through a barrel. I don't know which one I'm reaching into. And I pull out one of those absolute differences. Let me go back. Yeah. I reach into one of those barrels. I don't know which one, because I close my eyes and I have these elastic arms. I'm one of the 4 superheroes. And I have elastic arms. I pick a barrel and I pull something out of it. So before I open my eyes and look at what I have, I say, what's the probability that something that I pulled out of the barrel is a member of that convergent sequence? If that probability is 1, then xt converges almost surely on mu. Different from the convergence of the sequence of probabilities. Here we're looking at convergence of the sequence of absolute differences. I'm asking what's the probability that we could draw a sample that belongs to A. If that's 1, then we're done, and xt converges almost surely on mu. So there's a little bit of a difference between convergence in probability and convergence almost surely.
What you're calling almost surely, let's say it's in law.
No.
No, in law of distribution, right?
Convergence in law is convergence in distribution. We're going to get there in a minute.
I have a question. You describe consistency as
Convergence in probability. It's a large sample probability. A large sample property.
okay, and you describe it as in your sample.
It's asking what's happening to that convergence, that sequence of probabilities.
It's being equal to the population. How does that differ from unbiased?
Unbiased is a small sample probability.
So if something's biased, it's certainly not going to converge.
No, the maximum likelihood estimator of the population variance is biased, but it does converge in probability when true.